Assalamu alaikum. Bismillahirrahmanirrahim. Another video for chemistry second year students, and this is also about aldehydes, ketones. In this topic, we are going to discuss acid catalyzed nucleophilic addition reactions of aldehydes and ketones. Previously, we discussed base catalyzed nucleophilic addition reactions of aldehydes and ketones, and now we are going to talk about acid catalyzed nucleophilic addition reactions of aldehydes and ketones. Acid increases the electrophilic character of the carbonyl carbon and attack of the weaker nucleophile on the electrophilic carbonyl carbon becomes easier. So herein is shown general mechanism of the reaction. You can find here that this one is H, because it is acid promoted or acid catalyzed, so medium will have H positive and oxygen will have lone pair here. So oxygen through lone pairs attack on H positive, as a result of which O positively charged is formed, oxonium is formed. You are to write one other resonance contributing structure too, and that is I explain here. You put this sign which is of resonance, this one C O, and this here is H. Now C is positively charged. You are to write two resonance contributing structures there. This one is one and this one is another. When you imagine hybrid due to these two resonance contributing structures, you find that in case of this product, this carbon will be more electrophilic than this one. So when it becomes after protonation more electrophilic, then weaker nucleophile may attack here, and as a result reaction may become possible. You will discuss here three types of acid promoted nucleophilic addition reactions of carbonyl compounds. These reactions include nucleophilic addition of ammonia derivatives, polymerization of aldehydes, addition of alcohols with aldehydes. So these are three types of nucleophilic acid catalyzed addition reaction. But in your syllabus of polymerization of aldehydes, your reduced syllabus are polymerization of aldehydes and as well as nucleophilic. First of all, we are talking about ammonia derivatives addition. But before that, I think that these are some simple reactions that may not be ignored here. Three formaldehyde molecules are there. Sorry. Three formaldehyde molecules are there. In the presence of H2SO4, metaformaldehyde form. Just you are to keep in mind that this structure is like benzene. Three oxygen are there, two carbons are there, and along with three carbons are there, along with three carbons, two hydrogens are there. If one of these hydrogen is replaced, as in case is here, then we get paraldehyde. This is small scale polymerization that is possible in case of acidic medium. So we move on to next. That is main our concern, nucleophilic addition reactions of carbonyl compounds with ammonia derivatives. Ammonia derivatives are obtained when you replace out of the three hydrogens that are bonded with nitrogen with some other group like OH, like phenyl, like aniline, like urea. So you get derivative of ammonia. Two main things are here. What these main things are? Number one, this nucleophile is attacking at the carbonyl carbon, and OH is shifting from this NH2 to this oxygen. So OH is there, and in second step this HOH, this product is formed, and this HOH is further removed, and we get doubly bonded nitrogen with carbon, and oxygen is removed as water. So where G may be OH, these are derivatives of ammonia. When you replace this G with OH, when you replace this G with another NH2, when you replace this G with some aniline, then you get phenylhydrazine. This is, and when you replace this with the urea, you get semicarbazide. However, we move on to next slide. Addition of derivatives of ammonia and final product, and some examples again here, which you have already discussed there. NH2 NH2, NH2OH, NH2 semicarbazide, NH2 aniline phenylhydrazine, 2,4,6 dinitrophenylhydrazine. Hydrazine, phenyl, and carbon number 2 has nitro, and carbon number 4 has nitro. 2,4-DNPH abbreviation is there, 2,4-dinitrophenylhydrazine. Since this compound is important, it has been mentioned in your reduced label, so here is its elaborated formula. Hydrazine is this one, sorry. NH2 hydrazine, same with same ink is written in English as well as same symbol as used. Nitro present in red color, 2,4-dinitro, and phenyl of course black, written black, and shape is also black. 2,4-DNPH, 2,4-dinitrophenylhydrazine is there. Reaction with hydroxylamine, oxime is formed, ethanol aldehyde, and here is ethanol or acetaldehyde, hydroxylamine. As a result, ethanol oxime is formed. Acidic medium is there. Hydroxylamine in case of propanone, more commonly you call it acetone. So propanone oxime is formed there. Similarly, reaction with hydrazine, hydrazone is formed there with acetaldehyde and with ketone. These examples are. Similarly, phenylhydrazine is formed there with aldehydes or ketones. Here, reaction with 2,4-dinitrophenylhydrazine is then given. Aldehyde and ketones react with 2,4-DNPH in the presence of an acid as a catalyst to form yellow or orange precipitate, or 2,4-dinitrophenylhydrazone. The yellow or orange PPT precipitates are there. So this reaction is here. Carbonyl oxygen and NH2 two hydrogens are removed, and phenylhydrazine 2,4-DNPH 2,4-diner attached with carbon through double bonds. It has been further explained. This get lost, which has been encircled in red as water, and the other two bits just join together. 2,4-dinitrophenylhydrazone is formed with orange or yellow color. This slide shows different colors. On the left hand side is the reagent 2,4-dinitrophenylhydrazine, and on the right hand side you have positive tests for aldehydes and ketones, since the products precipitate as yellow or red solids. So these yellow or red solids on the right hand side indicating positive result for some aldehyde or ketone. This is important mechanism of ammonia derivatives and some carbonyl compounds. First step is the same, protonation here, as a result of which more electrophilic compound is formed. Now in the second step, nitrogen of ammonia derivative acting as a nucleophile with its lone pair attack on the more electrophilic more positively charged carbon, and as a result of which sigma bond is formed between nitrogen and erstwhile carbonyl and now protonated oxygen bearing carbon, as a result of which nitrogen becomes positively charged, and after that attack, this deprotonation will take place, and this hydrogen, you can see that no more is here, and deprotonation happens, and as a result, so first step is, and as a result this product is formed. So first step is protonation, to create strong electrophile. Second step is attack of nitrogen nucleophile of ammonia derivative to more electrophilic carbon, protonated oxygen bearing carbon, and deprotonation. And third step is again protonation of which was protonated first step, now again protonated here, and as a result OH2 positive is formed. Now you know that H2 is better leaving group than OH, so it will be removed, H2O, and deprotonation will take place, and as a result we get our desired product of the reaction of ammonia derivative with carbonyl compound. That is simple mechanism. 3 steps. First is protonation, second step attack of nucleophile and deprotonation, third step is again protonation, removal of water, and deprotonation from remaining hydrogen from nitrogen. Move on to our next oxidation reaction. That is another topic included in your reduced syllabus in your 2021 exam. Aldehydes and ketones. There are two types of oxidizing agents. There may be strong oxidizing agents like KMnO4 acidified, potassium dichromate, H2SO4, and dilute nitric acid. They can oxidize both aldehydes as well as ketones. Aldehydes are oxidized into corresponding acid, whereas ketones, here in this both aldehydes are given. Acetaldehyde is oxidized to acetic acid. Propionylaldehyde is oxidized into propionic acid. And oxidation of ketones is given. Same strong oxidizing agent can also oxidize ketone. Ketones, you know, are less reactive, and at the same time it is difficult for them to undergo oxidation. So only strong oxidizing agent can oxidize ketone. You have to keep in mind one thing, that carbonyl will be part of that chain which has fewer carbon atoms. That is, if you have two different chain lengths of alkyl group attached with carbonyl carbon, then carbonyl will become part of that chain which has comparatively fewer carbon. So in following case, for example, carbonyl will become part of this methyl, and you get acetic acid here. At the same time, other part is also has 2 carbons, so that would also be, I change color here, that would also be converted into same number of carbon containing carboxylic acid. So you have to keep in mind only this thing, so it will be easier for you. Now you know that in case of aldehydes and ketones, mild oxidizing agent do not do the same thing in both cases. They are do not undergoing reaction with aldehydes or with ketones, whereas can undergo oxidation reaction with aldehydes. Aldehydes are more reactive than ketone. So when this thing is there, it means that we can use mild oxidizing agent to distinguish aldehydes from ketones or ketones from aldehydes, etc. So mild oxidizing agents are tolerance reagent, Fehling solution, and Benedict solution. So these can oxidize aldehyde, but they cannot oxidize ketone, so they are used as a test. Here is given with some image. Fehling solution test, that is taken from your textbook. Fehling solution, mild oxidizing agent is an alkaline solution of cupric ion Cu+2 and sodium or potassium tartrate. Same tartrate which you discussed, 2,4-dihydroxybutane dioic acid in your optical isomerism topic. When Fehling solution is treated with this one, we get red PPT of cuprous oxide. So aldehydes are acting as a reducing agent, and the reducing agent is itself oxidized, so aldehyde converted into acid, and copper Cu+2 is reduced to Cu+1, cuprous oxide. So red color due to cuprous oxide, acid from aldehyde, and water OH is there. So in this way we get. Here in the image, Fehling on the left hand side is negative test. That is, you know, the copper is copper sulfate, for example, no blue color is there. So node, when there is no test, that is on left side you are observing a yellow color, whereas at the right hand side you are observing in case of positive test, that is reddish precipitates of cuprous oxide. So right side positive, left side negative. I am talking about this one is negative and this one is positive. Okay, I hope you will be clear. This is cupric oxide, this one is here. So I have written, I have taken from some other book, and a balanced equation. You may write this balanced version here, and you write here whatever you have written in previous. For example, you have written observing here sodium tartrate. You can write this sodium titrate here, sodium tartrate here. You can write sodium tartrate. Okay, and you have 2 here, you have 5 here, you have 3 here. It is balanced form, and that will be not violation of your textbook too. However, you are to write above the arrow sodium or potassium tartrate, whatever you are using. That is, I think, a better equation instead of the previous one. Once again, tolerance, ammoniacal solution of silver nitrate. Complex is formed diamine silver hydroxide, and first thing here is you are to correct it, because here you are to use outside this small bracket, outside ammonia twice 2. So Ag correction would be Ag NH3 twice here, and then you are right here rest of the things, and of course silver Ag plus 1. So it is correct version diamine silver hydroxide, and you once again get that this one is acetaldehyde converted into acetate, and diamine silver and hydroxide. Ammonia may be there water at one place. However, if the coefficients are okay, then you can write this equation. Otherwise, I am presenting another slide to have another way of writing this one. This is metallic silver mirror. This test is also called silver mirror test. Mirror is formed. So this silver is deposited along with the test tube sides, and you can differentiate aldehyde from ketone. For example, here you are observing 2 test tubes. On the right hand side, this one is negative silver, this one is negative one, and this one is, you are observing this one here, this one is positive one. If you have aldehyde, you will get in this way, and you went from this layer which is deposited on the sides of the test, you can wash your face if you watch carefully there. And here is transparent, so no test is taking place. So just I have explained you how you will observe in laboratory when you perform this test. Next is another way of writing this equation. Diamine silver is here, diamine silver is here, aldehyde is here, hydroxide is there, metallic silver that is deposited on the test tube, acid, ammonia and water. I think this equation is more close to the reality, so you should write this equation along with the equation given in your textbook. So once again, you are asked to differentiate between acetaldehyde and acetone. You are to write these tests. Acetaldehydes will not acetones will not undergo these reactions. They do not react with Felix solution, they do not react with tolerance reagents. Silver mirrors are not formed, and reddish color of cuprous oxide is not formed if you are utilizing some ketone acetone. But in case of acetaldehyde, both these reactions will happen, and you can easily differentiate and tell which one is aldehyde, which one is ketone. Thank you very much. I think to some extent this video will be helpful to you. Pakistan Zindabad. Allah Hafiz.